size and shape of peptide ions in the gas phase are an underexplored dimension for mass spectrometry-based proteomics. To investigate the nature and utility of the peptide collisional cross-section space, we measure more than 1 million data points from whole proteome digests of 5 organisms with trapped ion mobility spectrometry and parallel accumulation serial fragmentation. Cross-section predictions for the synthetic proteome tools peptides validate the model within a 1.4% median relative error. CCS values can now be predicted for any peptide and organism, forming a basis for advanced proteomics workflows that make full use of the additional information. The combination of ion mobility spectrometry and mass spectrometry extends conventional liquid chromatography, mass spectrometry by an extra dimension of separation, increasing peak capacity, selectivity, and depth of analysis. Recent advances have greatly improved the sensitivity of commercially available IMS devices, and the technology is now set for a broader application in MS-based proteomics. This has motivated researchers to develop various models based on amino acid-specific parameterization and physicochemical properties. To obtain a sufficient number of CCS values for deep learning, we trained and validated our model with complex samples of proteolytic digests and pooled synthetic peptides. Our study complements recent efforts in predicting properties of peptides on the basis of their sequences alone, especially those using deep learning for retention times and MS/MS spectra intensities. Turbulence is ubiquitous in the universe and in fluid dynamics. Understanding this phenomenon is crucial, however, due to limitations in experimental and numerical methods in plasma systems. A complete description of the turbulent spectrum is still lacking. Here, we present the measurement of a turbulent spectrum down to micron scale in a laser plasma experiment. We use an experimental platform, which couples a high-power optical laser, an X-ray free electron laser and a lithium fluoride crystal, to study the dynamics of a plasma flow with micrometric resolution over a large field of view. Here, we show results from an experiment where a laser-produced Rayleigh-Taylor unstable plasma flow evolves towards a possibly turbulent state. The main diagnostic, an X-ray radiography platform, coupling an X-ray free electron laser and a lithium fluoride crystal, allowed us to take time-resolved images with sub-micron spatial resolution over a large field of view. From the obtained radiographs, we extract intensity spatial spectra, which can be associated to velocity spectra. Two particular features of the previously shown spectra are worth discussing since they diverge from the usual turbulence theories. Those are the inflection between the low and middle spectra as well as the bump. Quasi-periodic eruptions are very high-amplitude bursts of X-ray radiation recurring every few hours and originating near the central supermassive black holes of galactic nuclei. It is currently unknown what triggers these events, how long they last and how they are connected to the physical properties of the inner accretion flows. Here we report observations of QPEs in 2 further galaxies, obtained with a blind and systematic search of half of the X-ray sky. This model could make QPEs a viable candidate for the electromagnetic counterparts of so-called extreme mass ratio in spirals, with considerable implications for multi-messenger astrophysics and cosmology. 2 follow-up observations triggered with the XMM Newton X-ray telescope confirmed the remarkable bursting nature of the source. The first observation found the source in a faint state for approximately 30 ks, followed by a sequence of 3 consecutive asymmetric bursts, possibly partially overlapping, which is behavior that has not been previously observed in QPEs. The second XMM Newton observation showed an eruption very similar to the first seen in Aero QPE1 XMM1 in terms of amplitude and luminosity, although lasting for greater than 40 ks, that is, for almost as much as the 3 in Aero QPE1 XMM1 combined. The second EROSITA QPE we have detected, Aero QPE2, showed similar variability patterns and X-ray spectra as Aero QPE1. It is associated with the Galaxy 2 MASXJ02344872-441935 and has a spectroscopic redshift of Z equals 0.0175. Despite the ubiquity of physical systems evolving on time-dependent spatial domains, understanding their regular and chaotic dynamics is still in a rudimentary state. While chaos implies that the system's behavior can be altered by small perturbations, this sensitivity proves to be useful for control purposes. Here we report on the experimental discovery of a novel mechanism to control chaos by time variation of the system size. Depending upon the rate of the latter, the chaotic state may be completely prevented. Our experimental observations are disentangled with theoretical insights and numerical modeling, which also reveals the ability to control spatio-temporal chaos, thus making the findings relevant to a wide range of natural phenomena. There exist numerous physical systems evolving on time-dependent spatial domains ranging from crystal growth, pattern formation on animal skin to quantum particles traveling in a time-evolving potential and galaxy agglomeration in the expanding universe, many of which exhibit chaotic dynamics. To illustrate how one can traverse the edge of chaos by varying the domain size, as a testbed we have chosen the Faraday waves phenomenon, which is a paradigmatic example in pattern-forming systems, known to exhibit temporal chaos as well. From measure to the amplitude envelope C, wave frequency omega-0, and phase are recovered and, accordingly, the Faraday wave's complex low amplitude U equals CEI is reconstructed. In the presented work we demonstrated, both experimentally and theoretically, the ability to control chaos by the system size variation. These findings may shed some light on spatially evolving biological systems and life, that require a healthy dose of chaos for proper operation and hence often balance on the edge of chaos as known from studies on cardiac and neuronal activity, for example.